Thank you for joining today. I'm very honored to chair this session today, Net Zero Upstream Processing Technology. My name is Burkhard Seifert. I'm part of the BHP Global Innovation Team. I'll first begin by acknowledging the traditional custodians of the land on which we meet today, and I pay my respect to the elders, past and present, and extend my respect to the Aboriginal and Torres Strait Islanders people here today. You might have noticed some changes to our agenda. Dr. Koji Saito from Nippon Steel Research Institute Corporation was unfortunately not able to join us because of the unfortunate passing of his wife. We have sent Dr. Saito our sincerest condolences, and our thoughts are with him, and we want to thank him and acknowledge for his contributions. We have 5 outstanding presenters today, and I encourage you to have a look at their bios, which you find online. I especially want to thank David Trotter for being available on a very short notice. You'll see that the sequence of the presentations is such that we build on each other, go into further details, and presenters also highlight some of the barriers, enablers, and pathways they are witnessing. We'll start with the general overview of processing technology for iron ore, various aspects, and we start with the fundamentals, the mineralogy, and then an overview of the emerging pathways of beneficiation that we observe. We'll then talk more specifically about the barriers and opportunities for green iron and steel. You'll then hear more about one of the promising pathways, which is leaching, and then we have a closer look at thermal pretreatment technology specifically. And finally, we go into a little bit more deep insight into this thermal energy storage as a way how we can get the energy from renewable energy sources for these processes. We'll start with Dr. Mark Pownceby, Principal Research Scientist, CSIRO, talking about emerging pathways to process low-grade iron ore. Please welcome Mark. Thank you.
Thanks, everyone. I'm very pleased to be speaking here. It's interesting, my title there. I know this is a high-temperature forum and you're all interested in green steel. It's not a mistake. We crossed that out. We're talking about green iron ore because this, of course, is the precursor for green steel. We need to have high-quality iron ore. And it was amazing to hear about the fact that anyone who's got a blast furnace in their backyard is relining nowadays. So I originally set this out thinking about DRI was the goal, but really it's probably the blast furnace. And the quickest way to actually decarbonise some of the things that are happening in the blast furnace is, of course, higher quality ore. So green iron ore, we reduce the impurities, which reduces the coke load and the slag load. So in this talk, I really haven't got a summary, but I just want to leave you with 4 key messages. So if you get nothing out of this, these are the 4 key messages, right? So 1, mineralogy is really important. People talk about grade, but it's mineralogy. This is what controls what happens in smelting, beneficiation, whatever. Scale is important. The Australian iron ore industry is, 800, 900 million tonnes shipped every year from the Pilbara, right? So if we're talking about upgrading that from 62% or 58 to 62% to something like 66, there's a huge volume there that we have to process. I don't think, and you'll see this throughout my talk, I'm going to give a more general overview and other speakers will go a bit more specific, but I don't think there's a one-size-fits-all approach to beneficiation. I think there'll be a number of different techniques. And lastly, as a confession, I lied to you because I'm a geologist, and mineralogy is the 4th key one. It really is important, and you'll see this throughout the talk. It's the key, I think. So, this is a bit of a history lesson. Let's start right at the very beginning. If you're on the Earth 4.6 billion years ago, which is when geologists date the age of the Earth, you would see perhaps, perhaps 4 continental regions. These yellow dots, they would be the stable platforms. The rest of the Earth would be covered by ocean. The thing about that ocean, and the geochemists would get really excited, is most of the iron is in there. It's not on those platforms. It's in the ocean. It's soluble in the ocean. However, around about 2.63 billion years ago, microorganisms came into existence that were able to produce oxygen. So the consequence of that was that the oxygen that was soluble in the seawater then became oxidised and was deposited. And of course, that's where we see our banded iron formations. So these are the original things which would have occurred around about 2.63 billion years ago. There's a range depending on where you are and what continent. So, I'm 60 years old and the ravages of time have taken its toll on me. Imagine 2.6 billion years sitting in the Earth's surface. Lots of things have happened to these iron ores. So we've gone for the original magnetite, chert type iron ores. We've had things like high temperatures. They've been subjected to high temperatures. They might have been buried. They've had fluids pass through them. They've had oxidation at the surface. And of course, all of that has contributed to what we see today. So we've gone from something that looks like what's on your top right, to the original, banded iron type formation, to something that we see down the bottom there, which is a maramamba type ore. So we've gone from a magnetite-rich ore to hematite-goethite-rich ores. And other things that have happened, so when we've gone to go on all these alterations, processes that have happened to the iron ores over time, there's a significant effect on chemistry. And I think Gus showed this slide yesterday, but it's worth repeating again that there are different types of iron ores out there. So the original high-grade iron ores discovered in the 50s, were at Mount Whaleback, Mount Tom Price, were probably these Brockman ores, these really high-grade, 60 to 67% iron, really low impurities. But as I said, over time we've had lots of alteration. We've gone from these really hematite, Brockman type ores to these maramamba type ores, which are goethite, hematite, martite dominated. And also we have things called channel iron deposits, which are weathered iron ore formations that are concentrated in channels. I know there is magnetite out in Australia, but relatively simple to process compared to hematite goethite ores. They're famous last words. Please don't come back and get me on that one. The other thing that we need to consider, though, is that, well, when we've had all this alteration, this has a significant effect on the texture of the iron ores. So in this slide here, the three that go down the left side are all hematite particles. This is reasonably high-grade hematite. The top one is really dense hematite. This would be your lump ore that we would be really after, really high grade. The bottom one is still hematite, but it's a lot more porous, and you can see the microscopic images of these. The top one's really dense, then the middle one's microplaty hematite, and the bottom one's really, really microporous. So that's sites where impurities can get in. On the right, we've got our other main component of Australian iron ores, which is goethite. And again, we get different textures in the goethite. We get really glassy looking goethite, which we call vitreous goethite, which is the top one, through to this thing which people sometimes call limonite or ochreous goethite, a really oxidised, impurity-laden material. Consequently also, there are effects on things like hardness. So our lump ores would be the high-grade, dense hematite ores or the denser goethite ores, whereas our fines are generated by the goethites and the really porous hematites. So we've got chemistry effects of the alteration over time. We've got textural effects. And if you look at ores in detail, and I suppose this is a real hobby horse of mine, mineralogy is the key thing here, because if you start to look at grade, you can easily tell what grade's doing. You just take a bulk assay. But really it's the complexity of the particles and the mineralogy of the particles which dictates how an ore is going to process, whether it's in comminution, beneficiation, or even downstream in a blast furnace. So if you look at the top left image, that's a typical Australian iron ore. The hematite is in the grey. The goethite is in various types of orange. And you can see there are some particles there. There's a hematite particle mixed with a bit of quartz. There's hematite mixed with kaolinite. You can also see that the goethite itself is really inhomogeneous texturally. It's got different levels of alumina in there, ranging from from about 0.7 up to about 5%. So this is the complexity that we're dealing with when we're talking about beneficiation of iron ores. And again, even if you look at the ones down on the right here, again, it's a hematite, goethite type ore. The hematite this is a backscattered electron image. The hematite is the bright particles and the goethite is the darker grey. And you can see that there's quite obvious correlations between the chemistry of what's in the goethite and the hematite with the actual mineralogy of the rock. So, for example, in G, we're showing the distribution of iron. So hematite is the brightest. There's iron also in the goethite. But when you start to look at other impurities like aluminium, which is in H, you can see that aluminium almost is exclusively in the goethite. Doesn't really report to the hematite. Phosphorus is in I, and so phosphorus is a key problem in Australian iron ores, and it also occurs primarily with the goethite. And you can notice that there's a correlation between phosphorus and aluminium. So, when you think about it then, we know that the ores have undergone this complex series of weathering, and we know that we can probably separate the hematite from the goethite in most cases, except for the case of liberation. So really, the solution's straightforward in theory. We just have to reverse that. So this is the challenge that I think a lot of my colleagues here are going to be talking. How do we reverse this to improve the quality of Australian iron ore? And again, when you think about it, nature gives us some clues. I mean, these ores have undergone fluid infiltration, hydrothermal processes, so maybe leaching, solutions will be the way, and Lina's going to talk about solutions and leaching are the way to reverse that and get us a high-grade ore. Also, these ores have undergone some form of metamorphism, so heating. So heating is a potential way to reverse it, and I think Alfonso is going to talk about, thermal beneficiation. So we've got some ideas, but it's still pretty challenging, and some of the challenges I think I've shown is mineral liberation. We've got quite complex ores, right? There will be environmental concerns we need to talk about, and again, I think Lina will discuss some of these things. Things like chemical reagents in leaching might be a problem. Thermal beneficiation is going to be fairly energy intensive, so we need to worry about that, but renewables might be the solutions. Water consumption in any process, particularly if we're generating a lot of fines, we don't want dust, we need, water's going to be an issue. And of course scale, which I'll talk about again at the end. So the key problem that I think I see here, and this is dictating why a lot of our approaches so far have been challenging, is the effect of impurities. And it depends on how your impurities are in the iron ore. If there is a discrete phase, like a clay in a aluminosilicate phase, or perhaps in the case of phosphorus, it might be absorbed onto aluminosilicate clays, we can probably separate that fairly easily using traditional techniques. They're discrete phases, they're not interlocked, we should be able to separate those. The problem arises when you see those grains, like I showed you, those goethite grains where we've got alumina and phosphorus actually within the structure of the grains. And that is a real problem. You're going to have to use some sort of technique that's going to break apart that structure, if you like. And so that's where you're going to have techniques like thermal beneficiation or leaching to really get in there and actually remove those impurities. And we'll get to those again in a little bit. So traditional approaches, work well in some cases. So gravity separation has advantages, and we use that all the time. We should be able to separate some of the really high-grade material in the lump by gravity. It's less effective for materials where there is really close density. There's not a great density separation. So you imagine goethite particles that go all the way from a nice clean goethite to a really altered goethite. Their densities are going to vary all over the place. So it's really difficult to actually get that split and say, get into a clean goethite versus a dirty goethite concentrate. We can do magnetic separation, and again, I think Alfonso will talk about that. And we can do things like flotation, and they have their advantages and disadvantages, but I don't think there's one technique at the moment that will do everything because of the mineralogy. So what are some of the new approaches? These are just some I'll talk about. So we've got magnetising or reduction roasting, leaching, goethite recrystallisation, selective breakage, and a semi-inverted hydrocyclone. The last three we're looking at CSIRO. We've looked at a bit of magnetising and reduction roasting in the past, but Alfonso is going to cover this today. And I'll really just talk about the green ones at the moment, just what we're doing and what I think the opportunities might be. So magnetising roasting basically works on the principle that you heat your ore up and you dehydroxylate the goethite, so you remove it, convert it initially to hematite if you do it under oxidising conditions. If it's under reducing conditions, you'll convert to magnetite. And the principle behind that is to exploit the magnetic differences between the gangue minerals and the iron ore minerals. It works really well if you've got discrete phases that are in there, so discrete gangue phases that will separate, and then you do your roasting, as I said, whether it's under oxidising or reducing conditions, you do a bit of grinding, and then you do a magnetic separation. And you can certainly upgrade iron ores that way. The real challenge, though, of course, is when you've got things like alumina and phosphorus and silicon in your goethite, right? It doesn't go to a discrete phase. When you dehydroxylate the goethite, it might rim pores, it might go to very small fine particles that you're just not going to get through straight magnetic separation. The other one we're working on is similar to a leaching method, and this relies on the fact that we know that a lot of the goethite is highly contaminated by elements that are actually in the structure of the goethite. Aluminium will substitute into goethite. It actually a direct replacement for iron, so that is a big issue, and you can get up to 15 mol% aluminium in goethite. Phosphorus is an interesting one where no one knows the mechanism of phosphorus incorporation, but it's always in there. We're trying to work that out. We think you can actually get it in, so you can actually substitute a small amount in. And the way this process will work, instead of actually leaching the ore itself, what we do is a goethite recrystallisation. So if you imagine when the goethite is forming, you've got fluids that are rich in phosphorus and aluminium and perhaps silicon, and then it crystallises a goethite which contains all of those elements. So here we're trying to reverse it. We're trying to recrystallise the goethite and actually eject the impurities. And there's certainly some promising work that we're doing around that we think might be very good in the future. Another one we're looking on is selective breakage. So remember I said we've got hematite, which can be really hard and dense. It can be quite porous. We've got goethite, which can be hard and dense and quite porous. So in selective breakage, we're relying on the fact that we've got these hardness differences. And so the aim around this project is well, we normally crush a BIF ore. So if we can crush it into different mineral types according to their hardness or softness, we might be able to separate these good versus bad components, if you like. And so we think the advantages of that is you can remove some of the barren gangue minerals or even hopefully some of the more impure goethites at an early stage, and you can do it dry. You don't need water, and we think it's the opportunity there where we can actually get rid of some of those nasty elements that we don't want. And I've got 2 slides to go, and I'm almost there, which is good. So this is just my sort of take on scale. And in this case, I'm using phosphorus. Phosphorus is a real problem in Australian iron ores, and the reason I'm using this is I think the scale of the problem is actually gigantic. If you look down in the bottom left, the spec for phosphorus from steel mills is around about 0.07 weight% phosphorus in an ore. And if you look in Western Australia, we've got at least 10 billion tonnes of ore that's 0.07 to 0.1% phosphorus. And we've got another about 8 billion tonnes that are greater than that. So we've got 18 billion tonnes that are out of spec. And we've got to process that. And we've got to beneficiate that. And we've got to remove those impurities. And just for the top left image is a 100 million tonne pile of iron ore superimposed on the Perth skyline. So we've got lots of those to process. So this is the real challenge, and it's the speakers up here, is how do we do that? And I'd just like to give you some brief thoughts, and I think my colleague Keith, we've had lots of discussions over the years. This is some work we did a few years ago, just looking at phosphorus in a high phosphorus Brockman ore. Just looking at the distribution of phosphorus in different phases. And you can see that quite clearly that phosphorus is concentrated in certain phases. And that gives us insights as perhaps that's where the opportunity is. We need to be able to separate those different phases out and process them separately. And so I think this is my final slide. So again, if we look at this, so that red line is where, that's the typical P impurity limit. So we've got, quite a bit below that, but we've got an awful lot that's above there. And this is only one ore type. It's probably worse in the Marramamba and some of the other ore types around. But if you look at right up the high end, 70%, this is perhaps okay right now for a DRI pellet feed. If we can just separate that, let's just separate that, send that out for a DRI pellet feed. This is the material we're currently shipping, it's the benchmark pricing. In a world where we're trying to decarbonise, we've got to upgrade that, so there are going to be opportunities. This lower material is the real target for the iron upgrade. What that process will be is possibly something like leaching, possibly something like magnetising roasting, but we can certainly upgrade that to a premium product. The real challenge, of course, is this one, the high phos. What do we do? It's probably going to be a two-stage thing where we get the P removal and then do the iron upgrade, or hopefully we can do it at the same time, because really, as I've shown, whoops, I'm almost there. As I've shown, if we remove phosphorus, because aluminium and phosphorus track pretty heavily, we're probably upgrading anyway. Once we start removing the phosphorus, we'll be removing alumina. So it could be a one process step where we're going to go all the way up from these high phos ores to a high iron product. And I think I'll stop there. Thank you.
Thank you very much, Mark. Maybe a quick reminder, if you've got questions, please use the Slido app, and we will wait then for the panel discussion later on. The next presenter is David Trotter. David is Research Portfolio Manager at the Minerals Research Institute of Western Australia. Welcome, David.
So hi, welcome to South Australia. So I'm going to do a talk on beneficiation of iron ores, but with a particular focus on how beneficiation affects the economics and the performance of green steel making. So I'll briefly talk about why we would want to make green steel, and then I have a map of Western Australia. Since we've already seen lots of maps of South Australia, I thought I'd put that in. I was actually going to put a map of West Australian wines on there as well, but I took it off after going to the Barossa on the weekend. I thought, can't compete. And then I work for Miro, and we've actually done a lot of modelling on green steel, supporting the government and its desire to do green steel making, but also do a lot of consulting with iron ore companies, particularly on magnetite and pellet feed. But today I'll mainly concentrate on hematite and goethite in terms of beneficiation. Let's see if we can get this to work. So I'll start with the slide. This is actually just some screenshots from the Mirror model, which is online. If you do a search of Mirror, M-R-I-W-A green steel, you'll get access to the free model. But it shows the pathway. And in the BOF route, I've just done an emission track of where the emissions are generated. So you might say, well, why are we worried about beneficiation? There is no emissions in this part. It's all in the agglomeration and iron making and perhaps a little bit in steel making. If you look at the EAF route, I've just got the one pathway here, fossil fuel EAF making. You actually do get a bit more of the emissions coming in the steel making section. But if you look at the scale using a DRI route, you actually do end up with lower overall emissions. It's just you get less in the iron making and more in the steel making. So this is where, when you start to talk about beneficiation, it starts to lever these aspects, which I'll get into. Before we do that, I'll put my map up. This isn't the wine region. This is the geological map, and this is a map of the Western Australia with just some indication of the green steel projects that we have ongoing, just to give you some context. So, of course, I've put our magnetite producers here. We've got CIDIC. In the Midwest, we've got Carrara, and we've also got FMG up in the Pilbara. We've also got a proposed pellet plant in the Midwest, which is under DFS. We've got Fortescue's DRI project up in the Pilbara. But around Perth, we've got many projects. We've got the Mirrors proposing a research facility and shaft furnace. We've got facilities at CSIRO. We've got Element Zero. We've got our Hazer H2 project, which is a demonstration stage. We've also got a hydrogen project, BP's hydrogen project. But we've also got a steel plant down in, it's down here, WA Green Steel, which is also reasonably well advanced on its approvals. So we do actually have a bit of a green steel infrastructure starting to emerge in Western Australia. So I think the opportunities to do beneficiation pilots and Mirror is actually also a sponsor of Lina's work is also possible, and we could add some beneficiation projects to this one. So why would we want to beneficiate? It seems like we don't. If you look at these slides, this is 2015 and shows you the silica plus alumina. And I know Mark talked about impurities, but the key impurities for iron ore are silicon or alumina. And this just shows the bubble charts of where the production is for BHP, FMG and Rio, all of which I've worked for at various stages, and shows you the silicon and alumina of each bubble as the size of the resource. Forecast for 2025, you can see we've moved to the right, and it's not just bits and pieces. Every year the average grade in the Pilbara is decreasing. So why is that? I think it's just a natural decline in the quality of the resource. It's also the equation in terms of cost of beneficiation versus return in the market. And having marketed iron ore, it's a very flat curve with Fe, so you actually don't get rewarded for making high-grade ores. So we might see that change in the future, though, as some of the low-grade ores may lose their market. So I've just put some indicative slides here, and you might ask, where did I get this data from? And I have worked for every iron ore company, so this data is for graphitic ore in the Pilbara, and producing about 180 million tonnes a year. So this is where this data comes from. But if you look at the different beneficiation strategies, you can look at a range of how much upgrade you're going to get. And you can see that the upgrade for graphitic ores just by crushing and grinding, maybe wind separation, gravity separation, maybe you've got some flotation, you get various upgrades. Then you go into the calcination, high temperature calcination, which I think our colleagues will talk about shortly. And then the new one, which is looking at thermal pre-treatment. So in girthitic, you're driving off that moisture to get an upgrade that way. But then Lina will talk about, I won't steal her thunder, but the benefits of using leaching process. So you can actually combine all of these things in various ways, and it is very dependent on the mineralogy. The cost also varies with process, and you need to do the techno-economics to work out how that increases in your sales price. I actually did have a map for phosphorus. I took it off because it's just flat. There is no benefit to phosphorus. But except I think Lina might have some solutions there, and she actually does get a benefit on the phosphorus side. So going into the opportunity for green steel. If we look at the cost of making green steel, if we want to make green ore, virtually our modelling shows virtually no difference in making a, if you like, renewable energy ore. In terms of green pellets, there is an extra cost of using hydrogen to make pellets, but not that significant. And actually, if you're using natural gas to make DRI, you actually get a cost saving compared to the blast furnace. If you're using hydrogen, however, to make DRI, you're actually getting a cost increase. And in the steel making section, you're adding 200 to 189, depending if you're using hematite or magnetite. So this can be problematic, and just shows you one of the issues you're up against when making green steel. How we get that extra cost back. So when we talk about beneficiation from our modelling, if you look at this black line shows you the actual, as you increase your gangue, and in this case the model includes water as a gangue element, so you've got to subtract the water, so therefore I can model for hematite and goethite. As you increase the gangue, you increase the actual levelised cost of green steel. So obviously with high grades, your levelised cost is going to be minimum, and with low grade it's going to be maximum. And then if you start beneficiating, you can, with a low grade ore, as you beneficiate, you're lowering your cost of green steel making through the EF. You reach a point, however, that you're actually going backwards. The actual cost of beneficiation exceeds the benefit. So in this case, at 10% gangue, which is actually about silica plus alumina, about 6%, the beneficiation actually doesn't lower the cost of green steel. So this actually equates to current Pilbara grades. So it's one of the reasons why the actual using current beneficiation methods, you actually don't get any benefit in terms of EAF steel making. So a very quick presentation. I'll let the others go into the details, but some key points we've found out. We do need further research capabilities for green steel, and so therefore Mira is proposing that in Perth we have a green steel research facility which will include the agglomeration, beneficiation, and hopefully we can directly put that into a shaft to test the economics of green steel making. Another thing we're trying to promote in WA is the use of green pellets, because it's a precursor to DRI. Also collaboration. We think that it is about the mineralogy, but it's not necessarily the mineralogy from one producer. So it might be a combination of ores, even magnetite hematite mixes, or hematite goethite from different producers. And if we were going to work out the best pathway to direct reduction, we need to make the best pellets we possibly can, not necessarily the highest grade pellets, perhaps the strongest pellets. So we need to do further research. So if you want any more information, you can go to our website, Green Steel Mirawa, or you can contact me. Thanks very much.
Thank you very much, David, for this great overview. Our next presenter is Dr. Lina Hockaday from Curtin University. Lina is a senior engineer, and her talk is about emerging leaching technologies, upgrades of iron ore for DRI production using chemical attack.
Hello, everyone. Notice how I avoided using the word hydrometallurgy in a high-temperature conference. We are using chemical attack. And most of the work here, I should say, is from two projects in the HILT CRC, Project 8 and Project 11 in the Program 1. So let's get into it. So I quickly gave you a literature survey. If you're a geek and you want to geek out, you can go and look at all the literature. But I can summarize for you what I tried to show there. If somebody reported that you mix an acid or a base with your ore and you include thermal treatment in it and it gave you a good result, I marked it green. If they said, it's okay, something else did it better, I marked it orange. Okay, so this is a range of literature spanning from 1964 till recently, and wow, that looks promising. Okay, but that's all laboratory studies. And why? Here's why. Okay, so let's compare the cost of doing beneficiation, and I grouped all the physical separation technologies that was mentioned, and I called it a generic physical separation. I say, okay, it's quite cheap. You only use $3.8 per ton to beneficiate it, 1 ton water, and tailings vary depending on mineralogy. We assume 40% tailings and 60% gives you a nice high-grade iron ore. Compare that to a historic leaching case where you had thermal treatment and a leaching reactor. Those conditions are sort of an amalgamation of what's in the literature, and then look at your cost. So you cannot make a profit. It doesn't work. Your caustic flakes is too expensive. You just can't do it. That's why nobody could get funding for a pilot. So what are we trying to do differently? And here I must say, I'm very much invested in this project. I run it, but it was not my idea. The big idea goes to Professor Ekstien, and he said, well, let's use what we've got. And I imagine standing on a red cliff looking at the ocean with the sun shining down and the wind in my hair. And that's what this project is all about. So we start with seawater. Seawater is already being desalinated all along Western Australia coast. So that's an established commercial technology. There's concerns about the seawater brines. They get pumped back into the ocean. They are higher salinity than the original seawater. But we want to use that brines as a feedstock for our reagent manufacture. We remove calcium and magnesium ions from the brine, and then we use a process called double membrane bipolar electrodialysis, or simply called salt splitting. And that's how I will call it from now on. Salt splitting takes a brine, and through moving it, the use of membranes, clever use of membranes and an electric current, you separate your salt into a base, sodium hydroxide solution, and acid, hydrochloric acid solution. The concentrations of the reagents in these solutions are dilute. They're about 5 to 6%. But we don't need caustic flakes. We need a caustic solution for our leach anyway. We were going to blend it with water anyway. And this is the breakthrough that we think makes this process possible. So here you can see in our process we also have thermal pretreatment. Thermal pretreatment we think is crucial to open up that mineral structure with cracks, give the leaching liquid more access to the impurities to dissolve them. And then when we do our caustic leaching, I should have said it in the previous slide, this is not including the neutralization of the caustic waste. So definitely it wasn't going to work. But we neutralize our caustic waste with the acid that we've produced, generating again a brine. On the way, we can also target several byproducts. At the moment, we've already demonstrated that we can make zeolites with that meets commercial specifications as for use in water treatment and probably as catalyst. We're further investigating geopolymers, which is calcium alumina silicates from the dissolved silicone alumina, which might be a supplementary cementitious material for the cement industry. And then we're also going to investigate if we can recover that phosphorus that we dissolve as a product. Phosphorus is severely needed in the fertilizer industry. There's a huge demand for it. The challenge is that the phosphorus we remove is still very dilute in solutions, and we'd have to find a way to make that work. So results in the lab, this is real laboratory results that just I'm showing here ore that was very amenable to leaching, the mineralogy checked out. It could be upgraded to above 67% on a calcine basis. This is a totally different ore with totally different mineralogy that was also very amenable to leaching. Similarly, we got it up to 66%. So definitely there's a lot of work in tailoring your leaching for the mineralogy of your ore, but we don't have time for that today. Let's discuss the bulk of the work we did in the last year. We worked very hard to take our complicated process and build a complete mass and energy balance, including energy efficiency measures and doing a pinch analysis to see how we could minimize energy. And we created 4 scenarios. So if you look at the little table A, B, C, D, those are the 4 scenarios. The brick-colored brick is always going to be your high-grade iron ore product. We would always aim to do that. It is our best product. But then the first thing that our engineering company, that's a partner in our project, told me is you must be able to run this without any byproducts. If your market for byproducts collapse, you should be able to run it just for your iron ore product alone. So we have that scenario. The blue drop is for maximum seawater intake or minimum seawater intake. So maximum seawater intake is going to also produce excess reverse osmosis permeate, which is potable fresh water that you could see as a secondary product. But if you don't have a market for that, you can minimize your seawater intake and recycle your brines and run it without maximum seawater or without selling water. That's where there's not a blue drop. And then the zeolites and geopolymers are where we aim to make as many byproducts as we can. So it's an indicator for the energy cost that goes into producing those extra byproducts. So comparing it to the same physical separation process that I compared original leaching processes earlier, you can see that we've made great strides in having a positive operating budget for this process. So This is, I think, a milestone for hydrometallurgy in iron ore beneficiation. Previously, we could see that it would be great if leaching was cost effective, but there was no way that it was. But with integrating salt splitting, we think that it may be feasible. So where to next? We can already see on this operating budget that the main cost inputs is mining the iron ore. So if we think of ways to avoid that, we have stockpiles of discard material from previous beneficiation operations, already crushed. Yes, they are even lower grade than the low-grade ores that we investigated, but the impurities are similar, silica and alumina, and we think that we should be able to remove those impurities as well. And in this process flow sheet, that would just give us more raw material for our byproduct production, which may even help. So in the year coming, we're also going to investigate tailings and slimes as possible feedstock for this process. And if you remove the mining cost, the budget would become more positive, even competitive maybe with other beneficiation technologies. The second, and actually the greatest cost, is electricity. There has to be a price we pay for unmixing seawater, and that price is electricity. Most of the electricity consumption goes into salt splitting. We have already applied energy recovery and like mechanical vapor recompression and energy conservation techniques to the flow sheet. I'm not saying it's optimized. I think I can maybe do it a bit better with more time, but this will increase electricity demand, and we have to be aware of that if we pursue this technology further. Good. So, we managed to get money to go towards a pilot. I think this is, again, a breakthrough for hydrometallurgy. We'll be doing 3 years of lab work, confirming operating windows, testing the leaching for specific partners in our project, partial integration testing. We have a lot of interlinked units. We'll start to see the interactions between them in laboratory scale. We're building skills. I will have 3 master's students starting next year, in addition to my current PhD student, and we'll build the understanding and the theoretical knowledge behind all of this and progress it. And through all of this, flow sheet optimization and the development of the techno-economic model is the main aim, and that will continue. Anything we learn in the lab gets directly applied to the techno-economic model, which will help us. Currently, we only have the operating budget. We do have a partner, BG&E Resources, that's our engineering company. They are busy with the CAPEX estimates for this process. It will probably be quite high. It's lots of units, lots of things that need to be on the flow sheet. So we'll see what we get when we get it, and we'll work through the process to see where does it go from here. There's a stage gate decision after 3 years to decide, is this worth piloting? If it is worth piloting, the engineering company will design that pilot plant ready to be built if the cost of that pilot plant is within industry appetite, if we can get funding for it. So that's where we are. But really, we can see that we have what we need. We have the iron ore, the seawater, the sunshine, and the wind. We're still working on what is the actual energy demand going to be. That is a process. We cannot cut corners and skip it. And to support the circular economy, we don't want to generate waste or future problems. We want to be as cognizant of the environmental impact as possible. We have to embrace the complexity of the idea, because if we want to do it responsibly, we can't just mix it, separate it, and throw the toxic stuff away. Then we hope that this can unlock the DRI processing route for many ores that has previously not been considered feasible. But even if it doesn't, it should be able to move many low-grade iron ores that's unsellable at the moment into saleable. It should provide low-phos ores that could be blended with other ores. So it has great potential. And in the last 30 seconds, thank you for everybody who believed in us, even when we didn't have a positive operating budget. You were willing to take a chance on us, HILT CRC, Arena, Mirawa, and also Curtin University. Thank you very much.
Yeah, thank you, Lina. It was fantastic to see your passion that you bring to this topic. Thank you. Our next presenter is Dr. Alfonso Chinnici. Alfonso is senior lecturer at the University of Adelaide, and he's going to present on an emerging thermal pretreatment technology that he's been working on.
Thank you, Burkhard, for the nice introduction, and good morning, everyone. So I'm very pleased to try and summarize in 10 minutes almost a 3 years journey that we have started with the HILT and the University of Adelaide around novel thermal pretreatment technology. So Lina has done a great introduction and overview of the novel leaching method, so I will try and summarize the work on the thermal treatment side. So before I start, before I forget, I would like to acknowledge all my colleagues that have contributed to this work, and also to all HILTs and the HILT partner that has provided kind support from the start around this new technology. Now, as Gus has probably highlighted in the first day, we've been working around a new way to provide heating for roasting. So Mark has introduced that thermal beneficiation has been around for quite some time. So what's new there is the way how we provide the heating to manipulate the chemical physical changes that we can provide to the ore. We do that through high flux radiation heating, the reason being that this can be provided through a series of renewable energy source. And as you can see from the slide, the idea is to try and provide the heating upstream so that we can also potentially soften up the material so it's easy to grind. And there is a lot of synergy with the work that Lina and Jacques are also leading at Curtin, because thermal treatment, of course, can be done in isolation, but there is a strong synergy also with downstream recovery, such as the novel leaching from Lina or more traditional magnetic separation. So today I will give you some result on that. Now, how we provide the heat? Of course, there is many ways to provide this high flux radiation. Here you see just a flavor of type of process layout that we can do. And you see also our radiant burner in operation that provide high flux radiation. Now, what's new? Roasting has been around for quite some time. There are 3 novelties that, together with Magaldi, I'm really pleased that the Magaldi team is also here in the audience, and Umberto is going to talk after me. Magaldi is a conveyor belt developer and supply, a global leader in the space. So we have joined force with them, and now they are also part of HILT. We end up patents a way to basically couple the high flux radiation methods with a conveyor belt as a way to heat pretreat a bulk material, although I would say this can also work for fine powder. And as I said before, the high flux radiation can come from different energy sources. We have strong insight at the moment of hydrogen combustion, but as you see from the drawing there, this can also be provided from concentrated solar thermal energy, resistive heating, or hybrids between those. And the other point of distinction is that this can be either provided in a calcining environment, also reducing, depending on the type of iron concentrates that you want. Here you see a snapshot of our lab scale facilities, a 10 kilowatts high flux burner. And I really would like to thank all of our industry partners to provide a series of low-grade iron ore. As Mark rightly pointed out, mineralogy is key, and how the ore responds to heat treatment is different depending on how mineralogy operates. So we have a variety of low grades but higher hematite, goethite, and goethite-rich ore, and some has high and others has low phosphorus. So we also wanted to check what happened to the phosphorus. Now, 3 research questions. The first was about, can we reduce the grinding energy? And we believe that for most of the ore that we have tested in the last 3 years, yes, we can. And as you can see, the high flux radiation method has a strong potential to reduce the grinding energy, on average up to 20%. One is a hematite being the primary ore. We have to roast up to 700 degrees, but when goethite is in the mix, this is really a mild heating in the order of 300, 500 degrees to reach this benefit. And as you can see also the way how we provide the heating, so fast heating from flux radiation versus slow heating has also an impact on how much grinding energy we can save. And you see that's kind of why this happened. Of course, when you have goethite, the goethite is transformed in hematite and release all of the OH radicals. This creates a lot of fracturing, but also the very fast heating creates additional thermal stress. So there is a strong damage that ends up basically making the material much softer and easy to grind. When it comes to the second research question is, can we upgrade the ore? And if yes, by how much? So you see, this is really depending on the initial mineralogy, but on average, the fast heating high flux radiation method was able to provide on average an upgrade of roughly 7% Fe unit with very good iron recovery. So we never had iron ore recovery, at least a lab scale less than 80%. So it was really a good achievement there. And also there was, when it's coupled with magnetic separation or with leaching, I have a slide on that, we are also able to really remove a lot of alumina, silica, and phosphorus. So we were able to prove that on average we can move from an uneconomic iron ore to an economic one, and potentially also start fitting in the region of the high grade region for DRI. The third question was about what's happening to the porosity. Porosity and surfaces is really critical, not much for the beneficiation upstream, but rather for the downstream. So imagine if we have this green iron concentrate for a DRI, or for example, if we need to have a leaching for further recovery, porosity is critical. So we were able to prove that with the high flux methods, we can really upgrade the surface area. By how much? Depending on the goethite contents, but on average, you can get up to 10 times the surface area increase. This has a lot of impact on downstream process. And on average, fast heating make a difference compared to slow heating rates. You see that, especially when goethite is in the mix, we can reach on average 30% increase in the surface area against traditional heating methods. Now, just to give you a flavor, and I kind of steal this slide from Lina, and again, I would like to thank Lina and Jacques from all the great work on the leaching side. So as part of one of the HILT projects, we have done some high flux radiation methods for pretreatment, and then Curtin has done the leaching. As you see here, that the fact that we have really high porosity and we are able to fracturing at the grain boundary really help the performance of the leaching. So if we do nothing, so no treatment, the ore really respond poorly to the leaching. But when we couple the new heating methods approach and we compare that to the performance of a slow heating rates roasting, there is an additional impact. So you see the phosphorus is further reduced, and also we can achieve for this specific one a 64%, 65% iron, compared to a 62% iron if it was heat treated through a traditional slow heating methods. Finally, we also, of course, start working more on the fundamental level, and we believe we start really scratching the surface of new way for goethite calcination. I don't have time to go into detail, but we have a poster, one of our students, Yucheng Lin, I think D23, she's really doing a great job on revealing some of this new calcination regime. So if you want to learn more, approach her during the poster time. And of course, the most important question, how much it costs. And I think David had a great slide about the trade-off between how much we beneficiate before it start impacting on the green steel production. So together with the partner, we look at, of course, using the experimental data to develop an Aspen process layout. And then together with Magaldi, we had some insight on pre-commercial data for conveyor belts. But you see that, of course, we had done a lot of scenario, but just to give you a snapshot of the outcome here, The beauty of the thermal treatment here is that can be provided either to natural gas or biogas, and also hydrogen and other source. Of course, from our current estimate, the levelized cost of beneficiation really depends on which energy source, the cost of the energy source, but also how fine you grind. You see, it's not, it's quite significant, the grinding energy to the total LCOB. But on average, we were able to show that the LCOB can be in between $12 to $30 per ton. That when it's compared to the current and also future market price for FE to China, this leaves still quite healthy profit for our partners. So we believe, of course, there is still quite a lot of work needs to be done on refining the techno-economics down the track, but this really gives us a strong framework to further develop and invest in the technology. Of course, as part of the HILT, we also support our technology development, and together with friend Alex and Swinburne, we have done work on their drop tube. You are very familiar, most of you, with the Calyx drop tube, but for this particular program, we looked, rather than using their drop tube for DRI production, rather as a calcination step, so without adding any reducing agent. And René has done, and one of our students has done a lot of work around this, so there is another poster, but story short for this is that Calyx drop tube can also be utilized as an upstream cleaning beneficiation technology. And in my view, there is also strong synergy between the moving bed technology and this downstream kind of technology. So in summary, with the support of HILT, I would say in the 2-3 years journey with Gus and the other, we were able to bring this technology of the moving beds, high flux radiation, roughly TRL3, and also pleased to let you know that we received funding to try and bring up in the next 3 years the technology TRL, hopefully 5 or 6. But for us, this is really a kind of a holistic technology. There is multiple benefits that can be achieved. Of course, the performance really depends on the initial meteorology, and is not to be seen in isolation. So there is also a lot of synergy that happen together with other downstream processes such as leaching. Thank you for the attention. Looking forward to the discussion.
Thank you very much, Alfonso. Our last presenter is Umberto D'Agostino. Umberto is Sales and Business Development Manager at the Magaldi Green Energy Company from Italy. Umberto will talk about steam generation with integrated thermal energy storage. Please welcome.
Thank you, Burkhard. Thank you, everybody. Good morning, and it's a pleasure to be here with you. Just a quick word on Magaldi. Magaldi is not a startup. It's an Italian company that was founded in 1929, so it's almost 100 years old now. And the core business of Magaldi is manufacturing conveyor belts for high-temperature materials. For example, there are several applications in coal-fired power plants for the extraction of dry bottom ashes from beneath the boilers, as well as other applications in foundries, steel mills, cement companies, and who knows, maybe in the future also pre-treatment of ores for mineral processing. But I will not be talking about conveyors for high-temperature material. I'll be talking about thermal energy storage and share our experience with thermal energy storage. In 2010, the company started to develop this concept of storing thermal energy in a fluidized bed of solid particles. And initially, this concept was applied to concentrated solar thermal. And then we further developed this concept for a system which, instead of using direct solar radiation, uses electrical heaters to charge the thermal energy storage. So it's basically taking variable green electricity in and dispatching steam as if it were a fossil fuel or a coal fire or a gas boiler. So just a quick look at the concentrated solar thermal power plant. This was deployed in Sicily because it's the area in Italy with the highest DNI. Of course, not as high as Australia, and also not as much space as Australia. Here we're on the premises of an oil-firing power plant. And this plant is innovative for a number of reasons. Of course, okay, we have the heliostats, that everybody has the heliostats. They are not innovative, even if we produce them ourselves. Then it has a secondary reflector, and then the direct solar radiation is entering the solar receiver, which is from the top, and the solar receiver is based on the ground. It's not just a solar receiver, because it combines 3 functions into a single piece of equipment. It's a solar receiver, it's a thermal energy storage, because it contains the fluid bed of solid particles, and also the heat exchangers are immersed in the sand. So also steam generation happens inside the same system. And now I'm explaining about the concentrated solar thermal because using the same solid media, the same supplier for the heat exchanger, the same air distribution system, the same external air-to-air preheater, we developed this Magaldi green thermal energy storage system, just adding electrical heaters in. It wasn't really just adding because it took a few years of testing to select the right ones. And this basically it takes electricity in, also variable electricity. We know if you want cheap and green electricity, it has to be variables. We haven't found a way yet to have it cheap, green, and fully dispatchable. So we believe it's more convenient to firm this electricity with thermal energy storage. We have seen yesterday that electricity for the foreseeable future, green electricity, will be variable. There will be a need for flexibilities. There will be services that can be also provided to the grid in case we want to do demand response or grid services with these systems. And at the same time, we see that the industrial processes that require high temperature thermal energy, they like stability. It needs to be dispatchable, it needs to be stable. And so this system is let's say it's a very boring technology. It's not so difficult, but it tries to solve a problem which is a big problem. So what is a fluid bed? Maybe you're all familiar with it. Fluid bed, there is no phase change. The sand is always solid, it stays solid. A fluid, it just means that there is some air which is injected from the bottom of the tank. It's a low velocity. It's 3 or 4 centimeters per second, just enough to allow a very smooth and a high thermal diffusivity across the bed. So anytime we are charging or discharging energy, the fluidization is activated. And when we just need to store energy, we switch off the fluidization. The sand packs at the bottom of the tank, of the vessel, and there is no auxiliary consumption, and also it is the sand itself that provides additional insulation. So this is, in a nutshell, the fluidized bed concept, the operation. Also, sand is stable well over 1,000 degrees. Although our experience operating this thermal storage is up to 620 degrees, this is not the limit of the sand, it's the limit of the metal that we selected for the heat exchangers, for the steam generator, which is immersed in the sand. Although this test is suitable also to be further developed to generate very hot air, although this is further along it's at a lower technology readiness level for us. So just like the CST, this system integrates into one tank the charging components, the energy storage, and the discharging components. They're all independently scalable, of course, up to a certain point. And outside, you see the air fluidization system. Maybe you can see it better in this concept diagram. So on the left-hand side, it shows the fluidization system. Basically, there is the hot air, which is coming out. It's used to preheat the ambient air coming in. And so there are no, let's say, very negligible thermal losses. And on the right-hand side, you see the steam generation system is a one-screw type with an external desuperheater, which is needed to keep the steam temperature constant, at the required temperature. The system is scalable. It's like a Lego because the main components are standardized because we have electrical heaters, a steam generator, and the air fluidization system, the manifolds. And we developed the engineering for a single module up to roughly 250 megawatt hours thermal. We like to think that we can build also much larger plants. We made a feasibility study, not a feasibility, concept study this year also for the reconversion of a coal-fired power plant, which was 7,000 megawatt hours. Of course, it will be a long time before we will have the guts to do that. Also because it's a private company with an appetite for risk, which is not unlimited, but we try to do one step at a time. So this is another plant that we have. This is Magaldi manufacturing facility where we produce the conveyors. And this is the pilot that we have in power to steam configuration. This is much smaller than the CST because really the reason for this pilot was to select the right electrical heaters. So we have this in operation since 2021. We tried both radiant panels and several suppliers of immersed electrical heaters. With the current, we are happy with the current configuration. It has been in operation in this way since October 2023. It's now 1 year. And after this plant, we already started the construction, the civil works of a second plant. This is 7.5 megawatt hours of thermal energy, thermal storage capacity, and 2 megawatt electrical of charging power. It will be charged by on-site PV and also by the grid when it will be convenient to do so. And this test will be supplying steam at 195 degrees to a company that is a vegetable oil refinery. It's actually the company that produces the palm oil that goes into the Nutella cream, chocolate cream. I don't know if you're familiar with that. Okay, so this is, I already talked. Beyond the direct electrification of thermal energy needs, we see that there are possibilities to integrate tests also with combined heat and power plants, which need to have a fixed relationship between the electricity and thermal power produced. It can be integrated in a number of ways, although we don't have yet a reference of a test system integrated with a CHP. So the conclusion is we didn't really invent anything new. We put together existing knowledge. To make it simple was not easy at all because it's now 14 years we've been playing with let's say with thermal energy storage systems. We don't know how the future will be. We understand there will be a need for flexibility. And we need all the tools. This is one of the tools, and we believe there is value. There are also other companies. It's not just us. We are happy to have competitors. In the end, if this kind of technologies develop and scale, it's because an entire ecosystem adopts them in some sense. All the engineering companies, the end users, the regulators understand them. So that's all. I think I finished. Thanks. Bye-bye.
Thank you very much to all the presenters. Really very insightful and very interesting presentations from all of you. Maybe let's give them another round of applause. Thank you. We've got now opportunity to ask the panelists questions. You see the Slido app instructions on the screen. I wanted to start off the questions by maybe summarizing one of the challenges that Mark has put forward, which is the challenge of scale. And you presented a way forward how you would, from a mineralogy perspective, you could have a more selective approach and then think about specific solutions, how you would target it. For all the other presenters, I also have got a question regarding scale in terms of the technology development, whereby you start off small, you maybe at the lower TRL. How do you think about you would be able to address that challenge that we're dealing with very large volumes and hopefully we'll have a solution in a relatively short amount of time?
Well, I wasn't sure the question was for me, but yeah, look, in terms of scale, as I tried to point out, I think the issue is more around, I'm not sure we have the separation technology yet to be able to produce the different products that need to go into other techniques. Now, like I said, I don't think there's a one-size-fits-all approach that we're going to leach everything. because I just don't think it's going to be feasible. I don't think we're going to heat everything. So we need to have some sort of technology, whether it's better magnetic separators. One thing I didn't talk about with dense media separation, but I think that might be challenging too, particularly for the fact that the high level of impurities sort of smear out the differences in SG. We might be able to do something, but yeah, I think it's up to Lina and Alfonso to say, well, you know, what sort of, I suppose, volumes do they think they can handle?
Thanks, Mark. And maybe I get Umberto to pick up on the conveyor belts. I think when we started this journey with gas around high flux radiation, we were trying to say which type of reactor technology will work best. And I think one thing we had in mind was we need to make sure that the throughput is high enough to match what a mine operation, especially for the iron ore player, looks like. So I think that's why we end up choosing the moving bed, because we believe that it can provide high throughput at relatively low cost, just because of the nature of where you have the moving bed. Single unit typically, I think you can process 2,000, 5,000 tonnes per hour, depending on the moving bed. So, of course, integrating with the heating is a challenge, and I agree with Mark. It's not going to be one solution to fit all, but potentially the moving bed could be part of the solution.
Yeah, scaling up is always a risky exercise. We have the potential to scale up. With conveyors, any new reference is a learning experience that pushes us to go a little bit further. And regarding thermal energy storage, it is designed to be scaled up, but also there, it's a learning experience. Also, scaling up in mining has a different meaning than scaling up in other sectors, because I saw the wheels of a truck there. They're not normal.
Yeah, the amount of iron ores that need to be beneficiated is intimidating. So what we did first, our first mass balance, we did one with almost looking at processing, was it like 120 million tons per year, I think, or 190. We looked at the ridiculous number, and we checked, can desalination be done at that scale? Yes, if it's like the largest plant in the world, is sort of that size. Can membrane technologies and salt splitting be done at that scale? The answer was they are modular and they can be stacked in multiples. Of course, it's going to be a ridiculous amount of multiples, but technically it's feasible. Can we build the leaching reactors? You can build really large leaching reactors. We are looking at not a heap leach situation, but a stirred reactor, meaning the reactions are a bit faster. And part of the research question is how can we reduce the residence times in leach tanks? Similarly, we run into a bit of difficulty with the byproduct crystallization. Zeolites require long residence times, but we're working on those technical challenges, and that's why it's research. It's research at TRL2. So we did a rough run through of what would it look like at a full commercial scale. Our partners dialed us back and say, look at a first commercial scale rather than a full commercial scale. Look at about 10 million tons a year. That is what our current flow sheets are doing. And we think that's probably a size that might be the first commercial plant if it ever does get built. But still, we cannot jump testing and demonstration steps. We have to go through the process and trust that TRL process. We can try and speed it up by doing some things in parallel rather than linear, but every step has to be gone through. So anything is possible. Whether it can be done, we're working on it.
Yeah, on the scale-up one, I think you're underselling the benefits of the technology because, for example, in a DRI plant, you might only need 4 million tonnes of ore. If you can get a 50% reduction in silica and alumina or a 30% reduction in phos, you might only have to treat 500,000 tonne or less and blend that in. And then it's a controllable element. On the phos side, there are lots of resources that are, say, around 0.15 phos sitting in the Pilbara. If you can reduce all those resources to 0.1 or blend in to get them under the sort of 0.12, suddenly they're saleable. So you might need to treat the whole 10 million tonnes. So, and should I answer I've got a Slido question, which is about the feasibility of producing pellets for BF and DR processing using Pilbara ores. Well, Pilbara ores is a big definition. There's magnetites in the Pilbara as well. But if we're talking about the normal goethite, hematite blends, yes, definitely. I think pelletized pellet plants should be looked at. We don't currently have a pellet plant in the Pilbara. But with pelletizing, if you're pelletizing goethitic ores, you need to have a longer duration process, etc. But you automatically get the calcine ore, so you're upgrading a 62, automatically upgrading it to a 64, 65 straight away, and dealing with the penalties of the water content straight away. Also, with Pilbara ore for DR, if we can get a 64, 65 pellet, I think you can make perfectly happy DR using that if the pellets are strong enough. If they meet the strength criteria, then it doesn't matter about the spec. We can certainly make HBI with 4 or 5% gang, and I can guarantee you there's a market, a 300 or 400 million tonne market for that product. There's plenty of HBI market. So you don't need to have 67, 68% to make green iron. Green steel's a different matter, and perhaps the smelter option we've got coming is being investigated, can still be economic at that 64, 65. So in that case, definitely Pilbara ores pelletised to make DRI would be suitable for smelting.
Thank you, Dave. Another question from the audience here is in regards to bulk sorting upstream to address the scale problem as well. Does anybody here have a view on sorting and bulk sorting? Mark?
Just some comments. Look, to be honest, I don't know the broad landscape, but just in terms of what we're doing at CSIRO in terms of trying to produce different products. As I said, we're looking at selective breakage, so which will allow us to sort into a higher grade, and concentrate the impurities in a different, softer type material. Some other technology we're working on is a semi-inverted hydrocyclone, which allows finer cut sizes, has the advantage of less water, but it's in the infancy stage, if you like, but certainly watch this space for what's happening there.
Fantastic. I wanted to think about the key enablers and maybe take a step back from this session and maybe look back a little bit on the previous one, which was around policy regulation and finance. And one of the things that I took away from that session was, obviously, for TRL, you need a factor of 10. A factor of 10 goes up in cost, and then you also need to be quite selective in the pathways that you chose. When we talk about iron ore in particular now and the complexity that's around, sometimes choosing the right pathway is quite difficult for companies. So I was wondering what approach would you take, and what are the things that you are looking for maybe from other stakeholders like government, other industries, community more broadly, industry, R&D, and so on? Like, what are key things that would help you to, or maybe help the industry and the R&D to make those decisions and embark on a pathway forward that's quite specific and selective?
The biggest one that I can see is when we're looking at iron ore processing is, you know, as you, no matter what you do when you're processing iron ore, you're using more emissions, you're generating more emissions, and I guess with the safeguard mechanism that's going to penalise you. So it's a way of accounting for the benefits you get downstreams, which are usually levered 5 or 6 times. So as you upgrade, you get downstream benefits and savings. How that gets accounted for and how that gets brought into the accounting equation.
I mean, from my view, I think what I can add is, you know, and I was showing the slide as well. You know, beneficiation would be, we need to look at, you know, low carbon, low energy requirement, low water. But at the end of the day, it would be an energy-intensive process, especially if you come from a thermal routes. But I think in the short term, if we are shifting toward DRI, this will help. Probably, you know, our scope 1, 2 emission will go up slightly, but this will have a strong impact on the scope 3. So I think it's kind of a slow but very important journey that we are on. Of course, in terms of what can be done on the R&D, to me, I think yes, there was some discussion from Greg around the hydrogen production and also the infrastructure requirement around hydrogen. So if hydrogen, you know, there's a lot of discussion about the cost. Yes, it's expensive, but if it's embedded in iron as a product that can be shipped rather than, I think this can really kick off a supply chain of global hydrogen. So rather than shipping the hydrogen or the ammonia, having the hydrogen embedded metals, I think that could be a critical pathway for Australia and for Pilbara, but also other regions like Whyalla. So I think from an R&D perspective, we do need to invest in, you know, looking at different strategy pathway, you know, how we can scale up the infrastructure, how we can reduce the cost of hydrogen while also bumping the volume of hydrogen that we have. Or the other things is in the short term, can we also start bumping biogas production? So, you know, that's potentially another way to de-risk the hydrogen routes. So while the hydrogen is still costly, if we can start having biogas in the mix, that could, you know, maybe unlock more traditional, for example, in the thermal beneficiation, having biogas as a starting point could unlock some, you know, supply chain while we get the hydrogen up and running at the right cost.
Thank you very much.
If I can just add, many of these beneficiation technologies are going to take a large amount of space, and we have to think on that. Will we have permission to build them from society? And we should think about it now rather than when we're ready to build it. We should be looking at what we can do to prepare for social acceptance of our ideas. So I just want to add that we must communicate to all stakeholders on that, because it's going to be a challenge to say we need this much land to basically make a soup with iron ore. It's going to sound ridiculous if we don't prepare people to be acceptable to the idea.
Yeah, thanks, Lina. Very valid point. Lina, I wanted to ask you a question regarding, or you elaborated really very clearly around the cost of leaching, the challenges that are associated with that, and that on its own it may not stack up compared to other technologies if you just in isolation look at that. And the approach that you've taken and shown is that you have a more holistic view and think about other elements that could include and should be considered so that the overall solution is more attractive. I'm interested in other cost benefits or cost reduction potentials that you are observing or you think about that could in future really further even improve those new technologies.
Okay, so I already mentioned that if we can use this as a treatment method for beneficiation waste, that would make it more attractive. But also, we still have to optimize our byproducts, the one byproduct being water. In the Pilbara, water is often a limiting step. So the flow sheet that we're developing gets all the water, and it does need fresh water, but it gets it from the desalination process. So seawater is the input. If we need fresh water to wash products or things like that, we get it from the desalination process. And you have access for the community. And here, this is maybe where the people operating in the Pilbara can give feedback. How valuable is that excess water that we can create? And that's something that we would like some feedback on, because it influences the flow sheet development. And then also our byproducts, we do think that as we study this project, we get more opportunities for synergies. Like at the conference last week, I had a PhD student approach me and say, what metals do you have in your brines? And I said, okay, well, here where we neutralize our acid that we have in excess, we have actually a magnesium chloride brine. And she said, oh, that would be perfect for metal organic frameworks to capture CO2. I'm like, well, yes, let's talk. So there are synergies that will become obvious as we talk to people and we relate our common needs. So, of course, more complex, but is it worth it? I would think it is. So please engage with us on that. Thank you.
Yeah, I think there's a lot of synergy with your technology if somebody's looking to build a magnetite plant, because they're going to need a lot of water, and if they're doing a desal, you do it in synergy with that. Use the brines from the desal to upgrade hematite, so you have a hematite and magnetite upgrade all in one.
Yeah, fantastic, thank you. One very technical question now, a couple maybe. This is for Umberto and probably also Alfonso. How do the heating elements survive in the erosive fluidized bed?
So this is called fluidized bed, but it's a very low air velocities. It's only 3-4 centimeters per second. And so on the heat exchanger, we operated that for 6 years. Then we emptied the sand, and we could see, we did a visual inspection, we could still see the strikes where the curves are. Regarding the heating elements, we tested several kinds of heating elements. The supplier of the heating elements, like all good suppliers, didn't want to provide, of course, any guarantees, because he said, no, we know that they last 7 to 10 years, but we use them with air, so we have no idea what you're going to do with this fluidized bed. But so far, so good with this, with more than 1 year of continuous operation. Of course, I cannot say that we had 7 years, 10 years, or 20 years of operation with these heaters. I don't believe they will go to 7 or 10 years, maybe less. But the single heaters, they can be easily removed. We don't need to empty the sand. We can pull them out from the top. Also, they really don't cost much. It can be considered as spare parts. So the honest answer, I don't know if they will last 5, 7 years, 8 years, I don't know. But so far so good, but they can be removed. So actually, we had a due diligence with a large oil and gas company in September, and they were, let's say, very confident, and they said, okay, you have been very honest regarding the heaters, but simply we don't have data for 5 years of operations with the heaters. But so far, we are confident. So, thanks.
Thank you very much. There's another question here. In the history of extractive metallurgy, leaching is normally reserved for lean ores, for example, heap leaching of lean copper ores, and pyromet is used for richer ores. Iron ores in the Pilbara are about 50%, and the question is leaching justified?
In the future, I don't think you'll be able to sell a 54 or 56 or 58, so there'll be no market for it. So you'll need Lina to get it to 62. Also, I think that your difference is that everything's in situ. In heap leaching, you're dealing with whatever's washed out. In this case, you're washing the ore always remains in situ.
I think it's justified.
I believe that as the final comment for today. So I want to thank the panelists, the speakers, presenters for all your inputs and the great work that you've done over the past years in showing the results in this forum. I want to thank the audience for participating, the great questions. Thank you very much.